Picture this. It's 1100 AD in Western India, and you're standing in what looks like an upside-down palace carved straight into the earth. Stone steps cascade down like a waterfall frozen in time, leading your eye through carved columns and shaded pavilions toward a pool of crystal-clear water far below. This isn't some ancient swimming pool for royalty. This is a stepwell, one of the most ingenious water storage systems ever created by human hands. You might think ancient people just dug holes and hoped for the best when it came to storing water. Wrong. These medieval engineers created architectural marvels that make modern water treatment plants look like puddles in comparison. We're talking about structures so sophisticated they solved problems our ancestors didn't even know they had. Cooling systems that worked without electricity, flood control that managed monsoon waters, and storage systems that kept communities alive through brutal dry seasons. Here's something that'll blow your mind. These stepwells weren't just functional, they were absolutely gorgeous. Imagine walking down steps carved with intricate patterns, passing through pillared halls that stayed cool even when the desert sun was beating down mercilessly above. The builders didn't just solve the water problem, they turned necessity into art, creating spaces so beautiful that people traveled for miles just to see them. But before we dive deeper into this incredible story, make sure you hit that subscribe button and give this video a like. And hey, drop a comment about what you found most fascinating about these ancient water systems. I always love hearing what catches your attention. Trust me, by the end of this video, you're going to have some serious opinions about medieval engineering. The story starts with something deceptively simple. Monsoon season. Every year, Western India gets absolutely hammered with rain for a few months, then nothing. We're talking about regions where you might get 30 inches of rain in 6 weeks, followed by 10 months of dust and scorching heat. It's like nature decided to play the cruelest possible joke. Here's all the water you need for the year, delivered in a couple of months. Take it or leave it. Most civilizations would have just built some basic cisterns and called it a day. Not these guys. They looked at this challenge and thought, let's build something that'll make people question reality. The stepwell wasn't just about storing water. It was about creating a complete ecosystem underground where people could escape the heat, socialize, and access clean water year-round. The planning phase alone was mind-boggling. Surveyors would stake out a perfectly straight axis from street level down to where they estimated the water table would be. This wasn't guesswork. These builders understood hydrology better than some modern engineers. They had to calculate seasonal water levels, account for underground drainage patterns, and figure out how to keep their structure from becoming a muddy mess when the monsoons hit. Once they had their line established, the real work began. Crews would excavate a massive trench, sometimes 40 feet wide and just as deep, with a square shaft at the deepest end where the actual water would collect. The amount of earth they moved was staggering. We're talking about thousands of tons of soil and rock, all moved by hand with nothing but basic tools and human determination. But here's where it gets really interesting. The stonework. These weren't rough stone walls slapped together with mortar. Every single stone was dressed, meaning it was cut and shaped to fit perfectly with its neighbors. The joints were so tight you couldn't slip a knife blade between them, and they did this without any mortar at all. It's like building the world's largest, most complicated jigsaw puzzle, except every piece weighs hundreds of pounds, and if you mess up, people die from thirst. The secret to their success was something called through staples, hidden stone ties that connected opposite walls, making the entire structure act as one solid unit. Imagine building a house where every brick was connected to the brick directly across from it. The result was a structure so strong it could withstand centuries of monsoon floods, earthquakes, and the gradual settling that destroys most ancient buildings. From the street entrance, visitors would begin their descent through what can only be described as a stone symphony. Long flights of steps dropped through shaded landings where people could rest and socialize. These weren't just functional spaces, they were architectural masterpieces, with carved parapets and railstones that kept feet sure during the descent. Every detail was planned, from the height of each step to the spacing of the landings. The pillared pavilions scattered throughout the descent served multiple purposes. They provided shade and rest areas, but they also played a crucial role in the stepwell's cooling system. The builders understood something about airflow that wouldn't be formally studied by scientists for centuries. Hot air rises, cool air sinks, and if you design your space correctly, you can create natural air conditioning that works better than anything we had until the 20th century. But the real genius was in the hydraulics. Side inlets brought runoff from carefully designed feeder channels, ensuring that every drop of monsoon water made it into the system. Overflow weirs prevented flooding by shedding excess water back to drainage systems when the stepwell reached capacity. And here's the clever part. A low silt trap at the pool's mouth caught all the dirt and debris before it could reach the main water storage shaft. This meant the water stayed clean for months after the monsoons ended. While other water sources turned into muddy puddles or dried up completely, stepwell water remained crystal clear. It's like they invented water filtration systems centuries before anyone understood bacteria or waterborne diseases. They just knew that clean water was better than dirty water, and they engineered accordingly. The structural system was equally brilliant. Instead of heavy stone vaults that would have required massive support systems, builders used simple stone beams supported by columns. This allowed them to span wide open spaces without the weight that would have made construction nearly impossible. The result was a sense of openness and grandeur that made these utilitarian structures feel like underground palaces. Light wells cut into the upper levels served a dual purpose. They provided natural lighting for people using the stepwell, but more importantly, they created a chimney effect that pulled hot air up from the depths while allowing cool, moist air to settle near the water level. Users could descend into what was essentially a natural air-conditioned environment, sometimes 20 degrees cooler than the surface temperature. The daily operation of these stepwells was a community affair. People would descend the steps carrying rope and bucket, drawing water from various levels depending on the season. During harvest time, when irrigation was crucial, some stepwells featured small animal-powered wheels that could lift water to surface gardens. Picture an ox or donkey walking in circles, powering a simple but effective water elevator that could transform barren land into productive agricultural space. What really sets these structures apart is how they turned a basic human need into a social and architectural experience. Drawing water wasn't just a chore, it was a reason to gather, to socialize, to escape the heat. The stepwell became the heart of the community, a place where news was shared, marriages were arranged, and children played in the cool shadows while their parents handled the day's water needs. The construction process itself was like watching a small army of specialists coordinate the world's most complex underground project. Master masons worked alongside quarrymen who could split stone with surgical precision, while surveyors constantly checked measurements to ensure every angle stayed true to their original plans. The margin for error was essentially zero. Mess up the water level calculations, and your entire community might die during the next drought. Stone dressing was an art form that would make modern sculptors weep with envy. Each block had to be shaped so precisely that it would lock into place with its neighbors, like pieces of an ancient Tetris game. The craftsmen used simple tools, chisels, hammers, and measuring sticks. But their results were so perfect that many stepwells still stand today, nearly 1,000 years later, with joints so tight they looked like they were cut by lasers. The most dangerous part wasn't the heavy lifting or the precise stonework. It was working in that deep shaft where the actual water collection happened. Imagine being 40 feet underground in a narrow stone tube, with monsoon water rushing in from multiple directions, trying to set stones while fighting against mud, flooding, and the constant threat of cave-ins. These workers were basically ancient extreme sports athletes, except instead of getting sponsorship deals, they got clean water for their families. Quality control was handled by master builders who had spent decades perfecting their craft. They'd inspect every stone, every joint, every measurement. If something didn't meet their standards, it got torn out and rebuilt. No shortcuts, no good enough attitudes. These guys understood that their reputation and their community's survival depended on getting every detail right the first time. The logistics alone were mind-boggling. Raw stone had to be quarried, transported, shaped, and lowered into increasingly deep excavations. Food and water for the workers had to be managed. Tools needed constant maintenance and replacement. Waste stone and excavated earth had to be hauled away or repurposed. It was like running a small city dedicated to one massive construction project. Weather played a huge role in the construction timeline. Obviously, you couldn't work during the actual monsoons. Trying to build stone walls while water is pouring in from every direction is a recipe for disaster. But the dry season brought its own challenges. Working in desert heat while handling heavy stone blocks was brutal, and the deeper the excavation got, the more dangerous it became for workers at the bottom. Some of the larger stepwells took decades to complete. Multiple generations of craftsmen would work on a single project, with fathers training sons in the specialized techniques needed for this unique form of architecture. The knowledge was passed down through families and guilds, creating a tradition of expertise that couldn't be found anywhere else in the world. The finishing touches were where these practical structures transformed into architectural masterpieces. Carved relief work adorned the walls, depicting everything from religious scenes to geometric patterns that seemed to dance in the changing light. Decorative columns featured intricate details that served no functional purpose except to make the space beautiful. It's like they decided that if people were going to spend time in these underground spaces, they might as well enjoy the view. Maintenance was an ongoing community responsibility that followed the seasonal cycle like clockwork. Before each monsoon season, teams would descend to clear accumulated silt from the water collection areas. Inlet channels needed cleaning to ensure proper water flow. Stone joints required inspection and occasional resetting when thermal expansion and contraction had loosened them over time. The annual maintenance ritual was almost ceremonial in nature. Community leaders would organize work parties, with different families taking responsibility for different sections. It wasn't just about keeping the water system functional. It was about maintaining community bonds and ensuring everyone understood how their survival system worked. Children learned by watching and helping, absorbing knowledge they'd need when they became the caretakers. Parapet repairs were particularly crucial because safety was paramount. A stepwell with broken railings or loose stones was a death trap waiting to happen. People descended these steps daily, often carrying heavy water containers, sometimes in dim light conditions. One loose stone could mean a fatal fall, so every surface that people might touch or step on received constant attention. The sophistication of the water management system becomes even more impressive when you consider the seasonal variations they had to handle. During peak monsoon season, a stepwell might receive more water in a single day than it would use in a month. The overflow systems had to handle massive volumes without washing away the careful stonework or flooding surrounding areas. Conversely, during the driest months, every drop of water was precious. The design had to ensure that even when water levels dropped to their lowest point, people could still access clean water safely. This meant calculating not just average water levels, but extreme conditions that might occur once every decade or generation. The cooling effect created by these structures was so pronounced that entire neighborhoods would organize their daily routines around stepwell schedules. People would time their water collection for the coolest parts of the day, turning the descent into a social gathering where news was shared and community decisions were made. It was like having a natural community center that also happened to provide life-sustaining water. Different step wells developed their own personalities and specialties based on their specific locations and communities. Some became known for particularly sweet water, others for their elaborate architectural details. Trading communities built step wells along caravan routes, creating networks of reliable water sources that enabled long-distance commerce across otherwise inhospitable terrain. The economic impact of these structures extended far beyond simple water storage. Communities with reliable step wells could support larger populations, more diverse agriculture, and specialized craftsmen who didn't have to spend their days worrying about finding water. It was like installing the infrastructure for civilization itself. Once you had reliable water, everything else became possible. The water itself tells an incredible story about medieval understanding of chemistry and biology. These builders figured out that different types of stone would affect water taste and quality in different ways. They selected specific materials not just for structural strength but for their ability to keep water fresh for months. Some stepwells used limestone that naturally filtered impurities, while others incorporated stones with trace minerals that actually improved the water's taste. But here's where it gets really wild. They discovered that certain combinations of stones would prevent algae growth and bacterial contamination. We're talking about people who had never seen a microscope. Yet somehow, they understood that the right stone mixture could keep water cleaner than anything available to most of the world until the 1800s. It's like they accidentally invented water treatment technology while just trying to build pretty walls. The depth calculations were absolutely crucial, and getting them wrong meant disaster. Too shallow, and your water source would dry up during bad drought years. Too deep, and you'd hit salt water or unstable soil that would collapse your entire structure. Master builders developed techniques for testing soil composition and water table levels that were surprisingly accurate. They'd send crews to dig test shafts at different distances from the main site, measuring water levels and soil types to create what was essentially a geological survey. Some of the most successful stepwell builders kept detailed records of their water level measurements over decades. They tracked seasonal variations, drought patterns, and long-term changes in the water table. This information was more valuable than gold because it meant the difference between building a structure that would serve the community for centuries versus one that would fail after a few bad seasons. The social dynamics around stepwell construction were fascinating. Wealthy merchants and rulers would compete to build the most elaborate stepwells, turning water infrastructure into status symbols. But unlike most royal projects, these actually served the entire community. It was like having a billionaire's yacht that everyone in town could use for their daily commute. The prestige came not from exclusivity, but from creating something genuinely useful for thousands of people. Women played a particularly important role in stepwell culture, since water collection was traditionally their responsibility. The design had to accommodate groups of women descending together, carrying heavy water containers, often with children in tow. This led to innovations like wider landings where people could rest and socialize, and carefully calculated step heights that wouldn't be too difficult for someone carrying a full water jar. The acoustics of these spaces were another unintended masterpiece. The stone walls and geometric shapes created natural amplification that allowed people to communicate across different levels of the stepwell. A woman at the water level could easily call up to someone at the entrance, and the stone surfaces would carry the sound clearly. Some stepwells became known for their echo effects, where a single voice could sound like a choir. But let's talk about the engineering challenges that would make modern contractors break out in cold sweats. Imagine trying to waterproof a structure that's designed to collect water. The walls had to be strong enough to hold back tons of earth and water pressure, yet permeable enough to allow controlled water seepage. They solved this with a technique called selective permeability, using different stone types and joint patterns in different areas. The load-bearing calculations were mind-boggling. Each level of the stepwell had to support not just its own weight, but the weight of all the levels above it, plus the dynamic loads of people moving up and down the steps, plus the hydrostatic pressure of water, plus the expansion and contraction forces from temperature changes. And they did all this math without calculators, using geometry and practical experience passed down through generations. Weather wasn't just a construction challenge, it was an ongoing operational concern. Monsoon floods could turn a carefully maintained stepwell into a debris-filled mess in a matter of hours. The overflow systems had to handle not just water, but everything the water carried: mud, rocks, dead animals, uprooted trees. Some stepwells included elaborate filtration systems that would separate this debris before it reached the main storage area. The maintenance crews developed specialized tools for different aspects of stepwell care. Long-handled scrapers for removing silt from deep areas, specialized brushes for cleaning carved stone surfaces, and measuring sticks calibrated to check water levels and structural alignment. These tools were often passed down through families like heirlooms, with each generation adding improvements based on their experience. Seasonal rituals around stepwell maintenance became community celebrations. The pre-monsoon cleaning was like a neighborhood block party, with different families contributing food, music, and labor. Children would compete to see who could carry the most buckets of silt up the steps, while adults handled the more dangerous work of checking structural integrity and clearing inlet channels. The economic calculations behind these projects were incredibly sophisticated. Communities had to balance the enormous upfront cost of construction against decades of reliable water access. They'd calculate not just the direct costs of stone, labor, and tools, but the economic benefits of supporting larger populations, enabling new agricultural techniques, and attracting trade caravans that needed reliable water sources. Some stepwells paid for themselves within a few decades through increased agricultural productivity alone. Reliable irrigation meant communities could grow crops during dry seasons, support larger herds of livestock, and engage in water-intensive crafts like textile production. It was like installing the economic engine that would drive prosperity for centuries. The technical specifications varied wildly depending on local conditions, but some patterns emerged across different regions. Typical bay spans ranged from 8 to 15 feet, allowing for structural stability while maximizing usable space. Course counts to dry season water levels usually fell between 20 and 40 rows of stone, depending on local water table depth and seasonal variation patterns. Master builders estimated that a medium-sized stepwell required moving approximately 3,000 tons of stone. That's about 600 elephants worth of material, all shaped by hand and lowered into increasingly deep excavations. The crew roles were highly specialized. Surveyors handled the precise measurements, quarrymen extracted and roughly shaped the stone. Dressing specialists created the final fitted blocks, and setting crews positioned everything with mathematical precision. The quality control process was ruthless. Every stone joint was tested by trying to insert thin metal strips between blocks. If the strip went in more than a fraction of an inch, the entire section got torn apart and rebuilt. This wasn't perfectionism for its own sake. Loose joints meant water loss, structural weakness, and potential catastrophic failure during monsoon season. Different regions developed their own architectural signatures based on local stone types and cultural preferences. Western Gujarat stepwells featured elaborate geometric patterns and slender columns. Rajasthani versions emphasized massive scale and fortress-like strength. Each style reflected not just aesthetic choices, but practical adaptations to local geology and climate patterns. The most impressive aspect of stepwell engineering wasn't any single innovation, but how they integrated dozens of complex systems into one coherent structure. Water collection, structural engineering, cooling systems, flood control, social space design, artistic expression, and community organization, all working together seamlessly. It's like they built Swiss Army knives the size of apartment buildings. Modern engineers studying these structures often discover details that weren't obvious even to the original builders. Computer modeling has revealed how the geometric shapes create optimal airflow patterns, how the stone selection affects water chemistry in unexpected ways, and how the structural load distribution allows these buildings to survive earthquakes that would flatten modern structures. Some stepwells included features that seem almost supernatural in their sophistication. Certain stones were positioned to create natural calendars, with shadows marking seasonal changes that told farmers when to plant different crops. Others incorporated acoustic properties that allowed whispered conversations at the water level to be clearly heard at the entrance, a security feature that let guards monitor activity throughout the structure. The construction timeline for a major stepwell typically stretched over 5 to 10 years, with work progressing in carefully planned phases. Foundation work happened during dry seasons, major excavation during moderate weather, and finishing work timed to be completed just before monsoon season, when the structure would face its first real test. Failure analysis was built into the design process through careful study of collapsed or failed stepwells in the region. Master builders would examine failed structures to understand what went wrong, then incorporate those lessons into new designs. This created an evolutionary process where each new stepwell was more sophisticated than its predecessors. The legacy of these structures extends far beyond their immediate communities. Stepwell technology influenced water management systems across Asia and the Middle East, with similar structures appearing in different forms from Afghanistan to Indonesia. The basic principles, underground storage, natural cooling, community access, proved adaptable to dozens of different cultures and environments. Today's water engineers study stepwells to understand how traditional societies manage scarce water resources without modern technology. Some contemporary projects in water-stressed regions have incorporated stepwell principles into modern designs, proving that thousand-year-old innovations still have relevance in our world of steel and concrete. The mathematics behind optimal stepwell design involved calculations that wouldn't look out of place in a modern engineering textbook. Structural load analysis, fluid dynamics, thermal transfer coefficients, soil mechanics, all figured out through practical experimentation and accumulated wisdom rather than formal scientific theory. These builders were essentially conducting advanced engineering research disguised as construction projects. But here's what really gets crazy about these ancient engineers. They figured out something that took modern science centuries to understand: the relationship between stone density and water purity. Different types of limestone and sandstone would actually change the mineral content of stored water in ways that improved both taste and preservation. We're talking about medieval builders who accidentally discovered water chemistry principles that wouldn't be formally studied until the 1900s. The quality control process was so intense, it would make modern construction managers look like slackers. Every single stone had to pass what they called the knife test. If you could slip a blade between two fitted blocks, the whole section got ripped apart and rebuilt from scratch. One loose joint could compromise the entire structure's ability to hold water, and in a desert climate, structural failure meant death for hundreds of people. The most mind-blowing part wasn't just the precision, it was the scale. Some of these stepwells moved over 5,000 tons of stone, all cut and fitted by hand with nothing but iron tools and human determination. That's like building a stone skyscraper underground, except every piece had to fit together like a three-dimensional jigsaw puzzle, designed by someone with a mathematics degree and way too much time on their hands. Temperature management was where these builders really showed off their genius. They discovered that certain stone combinations would naturally regulate water temperature, keeping it cool even when surface temperatures hit 120 degrees Fahrenheit. The secret was layering different stone types with varying thermal properties: dense stones that absorbed heat during the day and released it slowly at night, combined with porous stones that promoted evaporation cooling. The social engineering was just as sophisticated as the physical construction. These weren't just water storage facilities. They were community centers designed to handle hundreds of people safely during peak usage times. The step dimensions, landing sizes, and column spacing were all calculated based on crowd flow patterns. They understood human behavior well enough to predict exactly where people would congregate, rest, and potentially cause dangerous bottlenecks. Water quality testing in medieval times was basically advanced wine tasting. Master builders would train their palates to detect subtle changes in water chemistry that indicated problems with the stone lining or contamination from surface runoff. Some could identify the specific type of stone a water sample had been stored in contact with, just from taste and smell. Talk about a specialized skill set that definitely wouldn't make it onto modern resumes. The hydraulic calculations were pure wizardry. They had to figure out flow rates for dozens of inlet channels, each bringing water from different elevations and distances. Too much flow, and the system would overflow during heavy rains. Too little, and the stepwell wouldn't fill properly during short monsoon seasons. They essentially created hydraulic engineering formulas through trial and error, testing different channel sizes and angles until they got the math right. Seasonal maintenance required its own specialized workforce. Different times of year demanded different skills. Monsoon damage repair needed structural experts, while dry season cleaning required people who could work in confined spaces 40 feet underground. Some communities developed rotating maintenance crews where families would take turns providing labor, creating a social calendar based entirely around keeping their water system functional. The lighting system was another stroke of genius that most people completely miss. Those light wells weren't randomly placed. They were precisely positioned to provide natural illumination at specific times of day when water collection was most common. Early morning and late afternoon light would penetrate deep into the structure, creating a natural schedule that encouraged people to visit during the coolest parts of the day. Economic impact calculations show these stepwells were incredible investments. A major construction project might cost the equivalent of several years of community income, but it would increase agricultural productivity by 300 to 400%. Reliable irrigation meant multiple crop cycles per year, plus the ability to grow water-intensive crops that commanded premium prices in regional markets. It was like installing a money-printing machine that happened to also keep everyone alive. The construction workforce was organized like a medieval engineering university. Master craftsmen would take on apprentices who spent years learning specialized skills: stone cutting, joint fitting, hydraulic design, structural analysis. These weren't just construction workers. They were highly trained specialists whose knowledge was more valuable than gold. Some families guarded their stepwell building techniques for generations, passing down trade secrets that gave them competitive advantages in the construction market. Archaeological evidence suggests that successful stepwell communities could support population densities that wouldn't be matched in the region until modern times. Reliable water access enabled specialized crafts, increased trade, and complex social structures that simply weren't possible in areas dependent on seasonal rainfall. These structures were essentially the foundation technology that enabled urban civilization in otherwise marginal environments. The failure rate for stepwell construction was surprisingly low, considering the complexity involved. Historical records indicate that about 85% of completed stepwells continued functioning for at least 200 years, with many still operational after 500 years or more. Compare that to modern infrastructure, where bridges and dams are considered successful if they last 50 years without major repairs. Regional variations in stepwell design reflected local geological conditions in fascinating ways. Areas with soft sandstone featured wider steps and more gradual descents, while regions with harder granite could support steeper angles and narrower passages. The builders understood material properties well enough to optimize their designs for whatever stone they had available, proving that good engineering adapts to local conditions rather than imposing universal solutions. So there you have it. The stepwells of medieval India weren't just holes in the ground with fancy stairs. They were engineering masterpieces that solved water storage, cooling, flood control, and community organization all in one incredible package. These builders took the simple challenge of storing monsoon water and turned it into architecture so sophisticated it makes modern water treatment plants look like they're missing a few components. The next time you complain about your air conditioning bill or worry about water shortages, remember these medieval engineers who created sustainable solutions that kept entire communities thriving for centuries with nothing but stone, sweat, and absolutely brilliant problem-solving skills.